Hello and welcome to IB and A-Level Learning Center with Mr. Tai. In this video, I'm going to help you to solve the problems in AP Physics 1 2023 happening a few months ago in May. We are given here the table of the constants, the prefixes, and the value of the sine, cosine, tan, and the formula that we can use. Now let's start with the question 1 here. We can see directly on the diagram the cart is attached to the wall by a spring, and the initial position of the cart is here at the position x is a positive L, and the origin here x equals 0 is when the spring is normal, natural, meaning it does not extend or compressed. The cart is held at rest. When the cart is released, the system consisting of the cart and spring oscillates between the position positive L and negative L. The figure 2 shows the kinetic energy of the cart spring system as a function of the system potential energy. Kinetic energy and potential energy, so we have a linear relationship, can be expressed like y equal mx plus c, where m here the slope, which must be a negative value because the line is going down, is decreasing, and c is the y-intercept, which is 4 joule. So we have the formula of the kinetic energy is 1/2 mv squared, and the equation of elastic potential energy is 1/2 kx squared, where x is the expansion or compression, the deformation of the spring. We have a linear relationship like this, so the sum of these two types of energy is mechanical energy, and the sum must be a constant. Because if it is not a constant but decreases with time, the graph wouldn't be a straight line like this, but a curve. On the graph, kinetic energy versus potential energy shown in the figure, the value of x-intercept and y-intercepts are the same. 4 joule here and 4 joule here. You see that the maximum potential energy is also 4 joule, meaning the mechanical energy of a system is conserved. It probably explains why this is true using physics principle. We see that the maximum potential energy is 4 joule, the same as the kinetic energy, maximum kinetic energy. So this is because of the conservation of energy when the friction is negligible. Here, it is mentioned here. The friction is negligible. Mechanical energy of the system, which is the sum of the kinetic and potential energy, mechanical energy of the system is conserved. The next question, when the cart is at positive L and momentarily at rest, a block is dropped on the cart as shown in the figure 3. The block sticks to the cart, and the block cart system continue to oscillate between negative L and positive L. The masses of the cart and the blocks are m0 and 3m0 respectively. The frequency of the oscillation before the block is dropped on the cart is f1. The frequency of oscillation of the block is dropped on the cart is f2. After the block is dropped on the cart is f2. Calculate the numerical value of the ratio f2 over f1, frequency and the mass. Firstly, I'd like to emphasize that the collision between the block and the cart happens in the vertical axis. The force acting on the mass, the cart, is downward, and the force acting by the cart below on the block will be upward, obeying Newton's third law. And because this vertical direction is perpendicular to the horizontal direction, and therefore this collision will not affect the conservation of momentum in the horizontal direction. So we will also ignore the loss of energy, the change in energy during the collision. There's no energy going in or out of the system, and we assume that the energy of this system is the same. But because the mass of the system now has changed from m0 to 4m0 plus 3m0, so the speed of the oscillation must decrease so that the kinetic energy will be the same. For example, we have the O velocity v0 here square. This is the initial kinetic energy, and then when changing the mass to 4m0, the velocity must be a new value v, not v0 anymore, so that the maximum kinetic energy, this v0 is the maximum speed. So this new maximum speed of the system must be lower than the initial velocity. It will be half of the initial velocity, so that when you square it, you have the same kinetic energy. The question is about the ratio of the frequency, so we need to think of an equation for frequency. We are given here the formula for the period of the spring system, period. So the frequency is the inverse of this period, which means we have 1 over 2 pi square root of k over m. And according to this formula, we see that the frequency here is inversely proportional to the square root of the mass, meaning when the mass increases by 4 times, the frequency by 2 times. The frequency will decrease by 2 times. So let me write that formula here again. So we use the formula, the frequency f of a oscillator is 1 over 2 pi square root of k over m. Since k is a constant, for the first oscillation, f1 is k over m0. For the second oscillation, when the block is dropped on and attached with the mass, the new frequency is 1 over 2 pi square root of k over 4m0. Okay, so the ratio between f2 and f1, we take these two things and divide them. 1 over 2 pi simplify each other. So I will take this one, square root of k over 4m0 divided by, so I will multiply it with the reciprocal of this thing, ratio between k and m0, meaning this is m0 and this is k. And simplify this thing, k over k, we have 1/4, and the square root of 1/4 is 1/2. So this ratio is 1/2, meaning f2 is half of f1, which is the same with the argument that I made here. When the mass increases by 4 times, the frequency decreases by 2 times. The next question, I need to move to the page 4 down here. Question C. The dashed line in the figure show the kinetic energy K versus the potential energy U of the block cart spring system after the block is dropped on the cart onto the cart. This graph is identical to the graph shown in figure 2 for the cart spring system before the block is dropped on the cart, but now this is the new graph for the system with the block of the mass 3m0 on the cart. Okay, briefly explain why the two graphs must be the same using the physics principles. So we see that the relationship between kinetic energy and potential energy is a linear relationship, straight line. So the energy is conserved the same, as I already mentioned. And the answer to this, because the collision occurs in the vertical direction, there is no external forces acting on the system, but only the internal forces on the system. No friction, and also no friction. Of course, friction is considered to be external force, but only the internal forces of the interaction between the block and the cart when they collide, and therefore the total energy of the system, the mechanical energy, is the same, is constant. So the mechanical energy of the system is constant. After the block is dropped on the cart, consider a system that consists only the cart and the spring. On the figure 4, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped on the cart. To ask this question, we need to understand the two formula for kinetic energy, 1/2 mv squared, where v here is the new speed of the system, which is lower than the initial speed before the collision, and the mass m here is now 4m0, which is greater. So the speed v new here must be smaller than before. And secondly, the formula for the potential energy is 1/2 kx squared. We see that the potential energy here does not depend on the mass of the system, does not depend on 4m0, meaning the potential energy maximum will still be 4 joules. But when we only consider the kinetic energy of the cart only, without caring about the block, will have a certain part of the energy. This kinetic energy, 1/2 4m0 v squared, can be split into two parts. The kinetic energy of the block only, m0 times v squared, and the kinetic energy of the block 3m0 on the cart, 3m0 v squared. This part is 1/4 of the maximum kinetic energy of the kinetic energy, and this part is 3/4 of the kinetic energy. So the kinetic energy of the card only. This is 1/4 of the kinetic energy of the system. So the maximum kinetic of the card solely, only the card, will start from here, the value 1, because 1 is 1/4 of the 4 maximum, okay? And of course, it is also a straight line going to the maximum potential energy 4 joule, because this potential energy here does not depend on the mass. And of course, there's another graph like this, the kinetic energy of the block of 3m0. So the sum of these two lines indicating the change, the variation of the kinetic energy of the card solely and of the block, with the addition of these two types of energy will be equal to this original dashed line, the kinetic energy of the system. Okay, let's move on to the question 2 here. This is a problem about the motion of a card on an inclined plane. We see that the card starts from the top, the inclined position, initial position is x equals 0. The student conduct an experiment to determine the acceleration A of a card. The card is released from rest at the top of the ramp at the time t0 and moves down the ramp. The x-axis is defined to be parallel to the ramp. This is x-axis. The x-axis is defined to be parallel to the ramp with its origin at the top as shown in the figure. The student collect the data shown in the following table. So we have the position measured in meters and the time measured in second. The maximum position is 0.55 meter and maximum time is 1.2 seconds. Indicate which quantity could be graphed to yield a straight line whose slope will be used to determine the acceleration of the card. We need a straight line graph used to determine acceleration of the card. You may use the remaining columns in the table as needed to record any quantity. Do you remember, or you can check the formula booklet, the second or the third equation formula in that formula sheet? The distance that an object moves with a constant acceleration is s equal to ut plus 1/2 at squared, where a here is a constant acceleration, u is the initial speed of the movement of the object, which is 0. The card start moving down the incline, okay? And acceleration of this card is definitely a constant. So we need to use this formula, and because u is 0, we can simplify this formula into 1/2 at squared only, at squared. And therefore, to get a straight line graph, we need the two quantity on the axis like this. The quantity on the vertical axis, meaning the dependent variable, is the distance, and on horizontal axis, which is the independent variable, not the time, but the square of time, because we consider the square of time here is like a new variable w, so that the distance s is 1/2 of a times w, and w is the independent variable, which is t squared here, and the coefficient 1/2 a will be the slope, the graph, okay? And therefore, to get a straight line graph, we need to plot this following graph, and we'll have the data table represented on the graph like this, so that we can draw a best fit line which almost passes through the origin and very close to these data points, okay? So the answer, vertical axis is the position, and horizontal axis is the square of the falling of the time. The next one, on the following grid, plot the private quantities to create a graph that can be used to determine the acceleration of the card as it rolls down the ramp. Clearly scale and label all axis unit as a private. Draw a straight line that best represents the data. Okay, so we need to calculate the square of time here first. T square, the unit of course will be in second square. Calculate those things, huh? I can put those values into a sheet to make it faster, huh? This is the first column is the time. The square of time in the second column here will be this thing, huh? Multiply with Excel, or can type in the square here. Okay, this is the value, and we will take the 2 decimal places or 3 significant figures. So I will round it up to the 3 significant figure, huh? Meaning the decimal places is 2. Okay, here, and I will put these value into the table. 0.15, 0.35. Okay, so now let's start, plotting the graph, huh? On the vertical axis, it will be the position, visit position. The maximum value is 0.55, 0.1, 0.2, 0.3, 0.4, 0.5 here. 0.55 will be the maximum value up here. This is 0.5. Okay, let me put on those values. 0.3, 0.2, 0.1. You should have start from the origin from the bottom here, and go up. And this is the time squared. The square time. The maximum value is 1.44. 1.4 is here. 1.44 is very close to this point. Okay. The first point is when the position is 0.06, 0.02 here, 0.04, 0.06, 0.08. So 0.06 is here. 0.06. And the time squared, the square time is 0.15. 0.1 here, 0.2, 0.3, 0.15, 0.15 here. So this is 0.15. The first point will be here. The second point, the position is 0.14. 0.14 is here, this point. And the square time is 0.35. 0.35 will be 7 small square. 1, 2, 3, 4, 5, 6, 7. 7 4 here, 3, 6, 7, 7 here, 0.35 here. So the second point is here. Okay, and so on. Here is the last point. So you can see that these points aligned very well, beautifully, almost on a straight line. Possible to draw a line which almost passes through these points. Okay, it is not necessarily pass through all the points, but like this, and this is supposed to be the best fit line. Using the line you drew in part A, calculate the experimental value of the acceleration of the cart as it rolls down the ramp. Clearly scale and label all exit. Okay, we need to add the more detail to this thing. X measure in meter, and horizontal quantity is the square time measured in second square. We need to add these detail into the graph, indicating the scale and the unit. Using the line you drew in part A2, calculate the experimental value for the acceleration of the cart as it rolls down the ramp. As already mentioned, the value 1/2 A here in front of the square time. 1/2 A here is in front of the square time is the slope of the graph. To calculate the acceleration A will be twice the slope, 2 times the slope of the gradient. Okay, and we can calculate that slope by choosing any 2 points on the graph to make it easy for the calculation. So we should choose a point which is easy to read the values, such as this point. I choose this point A. Okay, its coordinates are the square time is 1.4, and the vertical value quantity position is 0.54. 0.54. And another point that I choose is here, so that it's easy to read the value. So this way, the point B, horizontal value is 0.4 for the square time, and vertical value is 0.2. Wait, sorry, 0.1, 0.1, 0.1 here, 0.16, 0.16, 0.16. Okay, now we can calculate the slope, taking the rise delta y over the run delta x. And do not forget to multiply 2 in front of it. Okay, the rise is 0.54 minus 0.16, and the run is 1.40 minus 0.40, and the value of the slope will be, we have the acceleration to be this thing, and we need to round it to 2 decimal places or 3 significant figure, which is 0.76. Question B. The students are asked to determine an experimental value for the acceleration due to gravity using their data. What additional quantities do the student need to measure in order to calculate the expected gravitational acceleration g from A? From the acceleration 0.76 here. So to answer this question, we need to know the relationship between free fall acceleration g and the acceleration of the cart A here. This cart moves on a slope as an incline like this. Okay. To find the acceleration A relationship with G, gravitational acceleration, we need to do the forces analysis. There are two forces acting the cart. Firstly, as normal, of course, is the weight mg, and secondly, the normal force Fn of the surface acting the cart. This normal force will be equal to this component of this mg. This component is mg times cosine of the angle theta here of the incline, and the other component of the weight is this component, the component that is parallel to the incline. So this downward component is mg times sine theta, and this will be equal to the resultant net force, because the normal force Fn here and this component cancel each other out. Okay, so this net force is mg sine theta, and it's equal to ma according to Newton's second law. So we can see that the exertion A is g times sine theta, because we can simplify m on both sides of this equation. Okay, so A equal to g times sine theta. To calculate g from A, we need to know the relationship g equal, according to the information that I wrote down there, A is g times sine theta. Okay, so g here is A over sine theta. So to calculate g, we need to know the angle. We need to measure the angle theta of the incline. And there are a few ways, different ways that we can do that. The first and direct way to measure the angle is using a protractor, and you put that protractor on the table and read the value of the angle that the incline makes with the horizontal direction. Okay, but to increase the accuracy of this measurement of the angle, you need to make sure that the table is perfectly horizontal. The second way that you can measure the angle is using a protractor like this. Use a string, a light and small string, attach it to the center of the protractor like this at this point, and a weight hang at the bottom of the string, so that when you put the protractor along the incline like this, the angle that this string, the vertical string, makes with this direction, the 90-degree direction, the direction that is perpendicular to the incline, this angle is the incline angle of the surface. There's also a third way that you can measure the angle, that is by using a ruler. You just need to measure the height of the incline h here and the length of the incline. You can measure the hypotenuse, which is also the distance the object travel, the distance s here, or you can measure the horizontal length of the incline like this, and then use sine or cosine. For example, you measure the length s and the height h, so that the sine of that angle theta is calculated by h over the length s along the incline, and therefore you can calculate the value of the angle. Okay, so there are three ways that you can measure the angle. So you can just need to mention that, measure the angle, or you can also measure the height. The next question, write an expression, the value of expected g in terms of A. I already written it here. Okay, so of course we should not draw it right here, but bring it down here. So the relationship between g and A, g is A divided by sine theta. The next question, the students calculate the value of g expected to be significantly lower than the accepted value 9.8 meter per second square. What is a physical reason other than friction of the air resistance that could lead to a significant difference in the experimental determinant of the value expected? Okay, according to the method of experiment, the slope is 1/2 of A. 1/2 of A, meaning A is twice the slope. This slope is calculated by the change in position delta x over the change in the square of time. Note that this is the square of time, not only the time. And because you square the time, so a tiny change, a slight change in the time will affect the accuracy of the experiment a lot. And measuring the time in this experiment is not easy. There are many ways that you can measure the time of this object motion at different position, because the position is very small like this. So you need advanced devices to measure the time, such as using a ticker tape, remember, or using a photo gate. Putting the photo gate at the two different positions. Let the digital clock start when the card moves through the first gate, turn the clock on, and then when the card go through the second photo gate, the digital clock is stopped automatically, and we can measure the time accurately. But the more challenging thing is measuring the time accurately. Okay, the measurement of time, which is the more challenging things, and also because the time is where it will be more significant in terms of making the experiment inaccurate, increasing the uncertainty of the experiment. Okay, or another possible reason is because of the mismeasurement of the angle, because the table that you use to carry the experiment out is not perfectly horizontal but slightly tilted. Question 2. Explain how the physical reason you identify in positive would lead to the decrease in the experimental determined value of G. You have the formula for G is A over sine theta, and the value that you calculated G here is smaller than the accepted value, which is 9.8 meter per second square. It is smaller probably because of one of the two reasons or both reasons. One thing is this acceleration A is smaller than we expected, or the second reason is that the angle that you measure is greater than the expected angle, because psi here is an increasing function. So if you measure the angle greater than the expected value, the final calculation, the value of G will be smaller than 9.8 meter per second square. The next thing, the students want to confirm that acceleration is the same whether the card rolls up or down the ramp. The students start the card at the bottom and give the card a quick push so that it rolls up the ramp and momentarily comes to rest. The x-axis is defined to be parallel to the ramp with the origin at the top, meaning the same definition of the origin with the first part of the question. On the following graph, sketch the position x and the velocity v as a function of time that correspond to the scenario y shown while the card moves up the ramp. Position visit velocity. Okay, definitely the velocity will decrease like this with a constant acceleration and keep changing linearly like this. The velocity becoming 0 here, and then on the top momentarily stop at the top and continue moving down in the opposite direction, rolling down because of the pull, the gravity. Okay, and the slope will be the same, and that slope is the deceleration of the car when it goes up, but becomes acceleration, speeding up the car when it rolls down. And position will decrease to 0 because we define the origin at the top, and the graph of position will be a parabola because position is ut plus 1/2 at squared. Note that this object is moving upward the incline, and the direction, the positive direction, is chosen to be the downward direction. The origin of the axis is on the top of the incline, and the positive direction is downward. This acceleration is actually the deceleration resulting from the component of the wave, which is mg sine theta, pulling this object down. So it is the deceleration, and the direction of the deceleration A here is downward along this axis like this. Okay, and therefore this deceleration is actually a positive value. Normally when we choose a positive direction going in this direction, then when an object slows down, the acceleration is the opposite, and normally the deceleration is negative. But in this case, because the positive direction is chosen to be downward like this, and therefore this deceleration is actually positive, and the initial velocity is upward like this, u, okay, going up the incline, and therefore this u is negative. So we have a quadratic function like y equal 2x squared with 2 here the acceleration, deceleration, and minus like 4x. So it's a concave up parabola like this. So the graph start from the maximum position here and go down parabola, and finally go back up again when going down the incline. Okay, this is the time t where it reaches here the top, meaning the velocity becomes 0 at the top, and we don't even need to draw this path of the graph where the cart goes down, roll down the incline again. A function of time corresponds to the scenario where the cart moves up the ramp, only when it moves up the ramp. Okay. Moving on, question 3. A small block of mass m0 is attached to the end of the spring. We have a rod here, a tiny rod that cylindrical. The natural length of the spring is L. The frictional force is negligible. Okay, this is very important information. Frictional force is negligible because whenever there is the existence of the frictional force, the problem will be a lot more complicated. At the time equal t1, the rod is spinning such that the block moves in a circular path with a constant tangential speed v1. Tangential speed, okay, we can illustrate that speed as this vector, which is tangent to the path, the orbit, circular orbit, and therefore it's called tangential speed, okay, v1. And then the spring is stretched a distance d1 from the spring unstretched length, as shown in figure 1. At the time t2, the rod is spinning such that the block moves in a circular path with a constant tangential speed v2, and the spring is stretched distance d2. And we can see on figure 2 that this d2 distance is greater than d1, meaning the string is stretched more, which means this object, the block, must be spun at a higher speed. So I'm going to roll a greater velocity vector v2 here. v2 is greater than v1. So what is the question? Question 1. On the following dot, which represent the block of the location shown in figure 1 and 2, draw the force that exerted on the block by the spring at the time t1 and t2. The spring force must be represented by a distinct arrow starting on and pointing away from the dot. Represent the block. Okay, draw the force. The force only, so it mentioned only one force, not the forces. And I think this force is the resultant, the net force. Because if we do not draw the net force, but all the forces acting on it, there will be 3 forces. Firstly, as usual, the weight. Secondly, the normal force, which is balanced, which is equal to the weight, and upward, Fn. So the 2 forces in the vertical direction here, Fn and W, will cancel each other out. Okay. Therefore, the third force, which is to the center of the rotation, the rod to the rod in this direction, this is the elastic force, Fe, and that elastic force will be equal to the resultant, the net force, because again the two forces in the vertical direction, they cancel each other out. Okay, so the only force that we need to draw is this horizontal force pointing toward the center to the right. So, because the question asks us only to draw only one force, which is the net force, so we don't need to draw the 2 forces, the weight and the normal force. Okay. As I already mentioned, in the second case, the second time t2, the object, the spring is stretched more, longer, extension, and therefore the force acting on it, acting on the block, this thing again is the block, okay, and this force is the elastic force of the spring acting on the block. This force is again equal to the net force, this is F2 equal to the net force in the second case, and it is greater than in the first case. Okay. Referring D1 and D2, describe your reasoning for drawing the arrows the length that you did in the part A1. Okay, so we're gonna explain why F2 is greater than F1. Reasoning, because the distance d2, because the net force is equal to the elastic force, which is proportional to the extension x. So the in the second case, d2 is greater than d1, so the net force in the second case is greater than the net force in the first case. Okay, I'm going to put a value 1 here. Greater than net force in the first case. Is the tangential speed v1 the block at the time t equal to 1 greater than, equal to, or equal to, less than or equal to the tangential speed v2 the block at the time t2? I already mentioned that v2 must be greater than v1. We're going to choose this one, and the justify the answer without using equation. Okay, to make the spring stretch more, to extend the spring more, requires a greater force, and that force is actually called the centrifugal force. But we do not study this thing. We do not mention the name of this force in the normal frame of reference, which is called the inertia frame of reference. We only mention about this force in a thing called the frame of reference, which has an acceleration, but mention that thing later. Require greater force, and so the spring, the elastic force of the spring, so the consequence is that the elastic force of the spring will also greater. Elastic force of the spring acting on the block will be greater, is greater when the time t2, when d2 is greater than d1. So with the elastic force greater, this elastic force is the centrifugal force. It is centrifugal force, which is proportional to the square of speed, and therefore when this centrifugal force is greater in the second case, the speed of this object must be higher, is proportional to the square of the speed, to v squared. So v2 must be greater than v1 when the elastic force in the second case, F net 2, is greater than F net 1. Okay. Question B. Consider scenario when the block travels in the circular path, the spring is stretched distance d from its unstretched length L. Determine expression for the magnitude of the net force F net exerted on the block. Express your answer in terms of m0, k0, L, and d, and fundamental constant appropriate. Okay, as already mentioned, this net force is equal to the elastic force k times x. X is the d here is x, okay? K times d. This is our answer, simply like this, and it of course equal to the centrifugal force, which is mv squared over r, where r is the radius, v is the speed. The radius is the sum of the natural length L and the extension d. Okay, this is mv squared. In the first case, the v is v1 and d is d1. In the second case, similarly, v v2 and d d2. But to answer this question, we only need to write down this one, k times d, where k is the k0. K0 is the spring constant, the stiffness of the spring. Okay, and the expression here is used for the next question too. Derive expression for tangential speed field block. Express your answer in the term of m0, k0, ld, and fundamental constant appropriate. So we need to derive expression for the speed of the object using this equation. Okay, so from this equation, v squared will be equal to k0d multiplied with the sum L and extension d, and then we need to divide this thing by the mass to get the speed square. Okay, so removing the square, we need to put a square root here. copy the expression for the velocity. And of course, you need to write this equation on the top here first, writing this equation first, and then write this thing later. Okay? Write this thing later. Two steps. Question C. Does your equation for the exchange speed of the block in part B2 agree with your reasoning from part A? Agree meaning when the extension is d2, when d2 greater than d1, we see from this expression that v, the velocity, is proportional to the square of the speed, and therefore it's proportional to the square root of the extension d of the spring, and therefore when this extension d in the second case is greater than the extension in d1, v2 will be definitely greater than v1. Okay, so you can answer that yes, explain your reasoning, because v is proportional to the square root of the extension, the speed v is proportional to the extension square root d. So when d is greater, the speed will definitely be greater. That's it. What's the next one? This is question 4, huh? Okay, so we have completed the 3 questions. Moving on, this is question 4. It is about moment of inertia and torque. A block of unknown mass is attached to a long lightweight string that is wrapped several turns around a pulley mounted on horizontal axis through its center. This is the axle and this is the center of rotation. The pulley is uniform solid disc, okay, it's a disc, and radius r given here. The rotational inertia of the pulley is described by the equation I equal 1/2 mr squared. The pulley can rotate about its center with negligible friction. Very important information here. Again, negligible friction. The string does not slip on the pulley as the block falls. When the block is released from rest and the block travels toward the ground, the magnitude of the tension exerted on the block by the string is Ft. Tension exerted on the block by the string, which means this is the tension here, acting on the pulley by the string, Ft, the tension. This is a given value by the problem. Determine an expression for the magnitude of the angular acceleration alpha d of the disk as the block travels downward. Express your answer in terms of m or ft and physical constants as appropriate. You can check the formula sheet again to get the equation for the angular acceleration. The angular acceleration alpha is determined by the torque T divided by the moment inertia I of an object, a rotatable object. Okay, it is very similar to an equation in the dynamic part, which the acceleration is the net force, the Newton's second law divided by the mass. So using this formula, we can write the equation for the angular acceleration. Alpha is the torque divided by the moment inertia. The moment inertia I is given here, and the torque T is determined by the force multiplied with the perpendicular distance r from the force to the axis of rotation, and that perpendicular distance is from the center, is drawn here from the axis of rotation to that force perpendicularly like this. So that distance, little r, that I wrote is actually equal to the radius. So we have the torque down here. That little r is equal to the big R, the radius. And this force is actually the tension, which is a given value, Ft multiplied with R. Okay, so plugging those things into this equation, the alpha acceleration of the disk is the torque, which is the tension force multiplied with the radius divided by the moment inertia given here, 1/2 mr squared. And now we'll simplify R on the top and the bottom. Ft 1/2 here, I will move the number 2 from the bottom to the top, number 2 here, and at the bottom, that is m and r. This is the final equation and the answer of this question. Moving on, scenarios 1 and 2 show two different pulleys. In scenario 1, the pulley is the same solid disk referenced in the part A. In scenario 2, hoop is a hoop that has the same mass m and the radius r as the disk. Each pulley has a lightweight string wrapped around it several turns and is mounted on a horizontal axle as shown. Each pulley is free to rotate about its center with negligible friction. In both scenarios, the pulleys begin at rest. Both strings are pulled with the same constant force Fa for the same time interval delta t. Those forces Fa here on the left and the right are the same, represented by the two arrows, two vectors with the same length. It is very important to note that they are the same in magnitude, and the time that they act on both objects also the same. After the time interval t delta t, the change in angular momentum of the disk is equal to the change in angular momentum of the hoop, but the change in rotational kinetic energy for the disk is greater than that of the hoop. Do you remember those two concepts? You know, the key of learning physics starts from understanding the definition, the concepts. We have two concepts, the angular momentum. In this AP Physics course, it is defined as the letter L equal to the moment of inertia I of an object. Moment of inertia is the sum of all the individual mass multiplied with the square of the distance from that mass point to the axis of rotation. For example, for the disk before, in the previous part of this question, we have I of the disk equal to 1/2 the mass of the disk multiplied with the square of its radius. Again, the angular momentum L here is defined as this moment of inertia I multiplied with the angular velocity omega. It is kinda similar to the definition of the linear momentum, which is P equal to the mass multiplied with the velocity. That is the first concept. The second concept is rotational kinetic energy. This rotational kinetic energy is 1/2 of I moment of inertia multiplied with the square of angular velocity. Again, I write that rotational kinetic energy Kr is 1/2 of I omega square, similar to the normal linear kinetic energy, which is 1/2 mv square. The next thing we need to explain why the change in angular momentum, and we're gonna call this change delta L. Both the pulley and the hoop are the same. So what is delta L? What is the formula to determine this delta L? Here, angular momentum L is I moment inertia multiplied with omega angular velocity, and delta L here. So this is the key, delta L, the change in angular momentum. Do you see that it is very similar also to the formula of the normal momentum? The change in momentum is equal to the impulse, which is the force multiplied with the time. So here, the change in angular momentum is equal to the torque multiplied with the time interval delta t, normally very short amount of time. We need to prove that the change in angular momentum here is the same for both objects, and apply that formula, the torque multiplied with the time interval delta t. So to prove that the change in angular momentum of both objects are the same, we need to prove that this thing, the torque, is the same, and the time interval is also the same. The second thing, delta t the same, was already given here, same time interval, so we don't need to prove that anymore. About the torque is defined as the force multiplied with the perpendicular distance drawn from here, the axis rotation, to the force, which is this distance, the little r. Okay, similarly with this one, so we see that the perpendicular distance r for the both objects are the same and equal to the radius of those objects. We can write the explanation of this question as follows, which are the results. So those torques are the same, and the time interval also the same. The time of action that those torque acting on both objects the same. Okay, and the time are also the same. So it is a little bit long, but we need to make sure that it is accurate. It has enough information. The second thing is that we need to explain why the rotational kinetic energy is greater for the disk. The next thing that we need to explain is why the rotational kinetic energy of the two objects are not the same, even though their change in angular momentum are the same. The rotational kinetic energy of both objects are different because of two reasons. Firstly, the moment inertia I of the two objects are different, and secondly, the angular speeds of those objects are also different. Okay, so both things I and omega are different. Why? Because I, the moment of inertia, represent the resistance, the inertia of an object in rotational motion. Meaning, if an object has a greater moment of inertia, it is harder to make it rotate. It is harder to accelerate it when rotating, starting to rotate or slowing down from rotating. For the disk here, it is a solid object, and for the hoop here, it is empty inside. They have the same mass, but the distribution of the mass are different. The mass of the disk distribute uniformly on the disk, the solid object, while the mass of the second thing, the hoop, distribute around the outside loop, and the inside is empty. And according to this formula, or you can use according to this formula, the distance from the mass points for the second object here, the hoop, will be greater than the distance from individual mass points on this solid object, which means that the hoop here will have a greater moment of inertia, meaning it is harder to accelerate the hoop. Okay, so the point is that the moment inertia of the two objects I are different, and therefore under the same effect of the torque, we know that the angular acceleration alpha is the torque divided that the moment inertia, and because there's a difference in the moment inertia I, even though the torque is the same, and therefore the accelerations are different for the two objects. Different acceleration result in different angular velocity, omega 1 and omega 2, as long as I1 is different from I2, and therefore rotational kinetic energy of the two objects are different. Moving on to question 5. A rod with a sphere attached to the end is connected to horizontal mounted axle. Here we have this is a disc, this is an axle, the rod is here, and the sphere is here, and this circle with the X symbol inside is the center mass of this system. This system is carefully balanced so that it is addressed in a position vertically upward from the axle. The center mass of the rod sphere system is indicated with the symbol as shown in figure 1. The sphere is lightly tapped and the rod sphere system rotates clockwise with negligible friction about the axle due to gravitational force. A student takes a video of the rod rotating from the vertical upward position to the vertically downward position. The figure 2 shows 5 frames, meaning they're still shots, that the student selected from the video. Note that these frames are not equally spaced apart in time. So let's look at these frames very carefully. We see that the orientation, the position of the spheres are different. So what is the question? The question is down here. Okay. Use the frame in the video shown in figure 2 to answer the following questions. In which frame the angular acceleration of the rod sphere system the greatest? And justify your answer. Angular momentum. The question is angular acceleration is alpha equal to the torque divided by the moment inertia. We don't know the moment inertia specifically, meaning an equation or a value, but we know that this thing is a constant. Okay, so this angular acceleration is the greatest when the torque is the greatest. And among the 5 frames, the torque here is the greatest when the torque is greatest when the torque is defined as the force multiplied with the perpendicular distance from the axis rotation to the force. So in these cases, we will draw the forces. This is the center of mass of the system. So all the forces acting on this object can be represented by a single vector, the resultant force acting on this system center of mass of the system. Okay, this is the force, which is the weight, gravitational attraction of the Earth. So in the first case, the frame A here, this W passes, the force passes through the axis, and therefore the distance from the axis to this force is 0, and therefore the torque in this case is 0. Okay. In the second case, the weight, the force is here. This is also the net force, okay, because there is no other forces. It rotates because of the action, the effect of this weight, the gravitational pull solely, okay, only. So the distance from the axis is here, from this point toward to the weight is this distance r. Similarly, in the third case, the frame C, the force W is here. So the distance is this one. And compared to other cases, you see that this distance will be the maximum because it is perpendicular to the weight in this direction. Similarly, this is the weight. You need to draw these weight W vectors are equal in the length, okay? And the distance is also determined from the axis to this line of action of the force, which is this distance, which is almost the same with this case. Okay, but this distance is definitely smaller than the maximum distance here. So the answer to this question will be definitely with frame C. Okay, similarly the last one, W is here, the distance is 0 and the torque is therefore 0. So the answer to the question 1 is in the frame C. This question weighs only 7 marks. So I think for this one, A1, we do not need to explain very detailed. We just say the frame C because the torque is greatest. The torque T is greatest because the distance is greatest. Okay, the distance R is greatest also. That is the reason why the torque is greatest. Question 2. In which frame the rotational kinetic energy of the rod sphere system be greatest? Briefly justify your answer. Rotational kinetic energy 1/2 moment inertia I multiplied with the square of the angular speed. Which frame this speed is greatest? It takes time to rotate. The torque will provide result in an acceleration. Acceleration is the torque divided by the moment of inertia. Okay, and therefore in the last frame, because the last frame is when the sphere is at the bottom, meaning the lowest position, and therefore the time for the rotation from the top sphere, the position of the sphere on the top here to the bottom, that time is the longest time, and therefore we have longer time for the speed to increase from 0. This speed increase from 0 to the maximum value, and the maximum value will be at the lowest position in the frame, the last frame. So at the lowest position, the height h here is minimum, the potential energy is minimum, and therefore the rotational kinetic energy is maximum. Okay, so the answer will be definitely the frame E. Moving on to the last question, B. The Ross sphere system has a mass big M and length L, and the center of mass located at a distance 3/4 L from the axle, shown in figure 3. Derive an expression for the change in kinetic energy of the Ross sphere system from the moment shown in the frame A, meaning when the sphere is on the top, to the moment shown in the frame E at the bottom. Express your answer in terms of ml and fundamental constant as appropriate. In the frame A, the sphere is here, and the position of the center of mass is here. That center of mass distance to the distance from that center of mass, to be a little bit lower here. The distance from the center of mass to this axis of rotation is 3/4 L also. We would choose the lowest point here at the position of the center of mass, the lowest position here at the zero level of potential energy. Zero level of the potential energy, PE. Okay, so the initial potential energy on the top here is M, which is the mass of the system, multiply with G and multiply with this is big M also. Okay, mg times the height, which is this distance, meaning 2 times of 3/4 L. That is 3/2 L. Okay, because double the distance 3/4 L. This is the initial potential energy. Okay, and this amount of potential energy will convert totally 100% into the rotational kinetic energy. So we have initial potential energy will be equal to the maximum rotational kinetic energy, meaning mg times 3/2 of the length L will be equal to 1/2 of the moment of inertia I times the square of angular speed. But we do not need to write this formula, we just need to write that this is the kinetic energy, rotational kinetic energy. From the moment shown frame, express your answer in terms ml and fundamental constant appropriate. Derive first on the change in kinetic energy. Okay, so this whole thing will convert 100% into this kinetic energy, and therefore the change in that kinetic energy, expression of the change in kinetic energy. Okay, the change in kinetic energy is equal to this thing. So I'm gonna replace the letter, the KE here by the delta, indicating the change of kinetic energy. Okay, this is our answer, mg times 3/2 L, or we can simplify that by bringing the 3/2 to the front. Okay, meaning delta kinetic energy change is equal to 3/2 mgl. The last question, briefly explain why the rod and the sphere gain kinetic energy if the Earth is not included in the system. Even if the Earth is not included in the system, when we say the thing about the potential energy, we didn't say it, accurately, the true meaning of potential energy. Potential energy actually the interaction, the energy due to the interaction between objects in a system. The gravitational potential energy, mgh, is because of the interaction, the pull of the Earth, of the magnetic field on the object. And therefore, the true definition of potential energy must be the potential energy of the system, the Earth and the object. This potential energy transfer from the Earth to the object, so that the total energy of the system, the Earth and the object, is the same. But normally, to simplify the concept, the law of energy, we usually just ignore saying mentioning the Earth in the system, and we can answer this question as follow, that the gravitational force does the work. That is it for the solution of the whole free response question part in AP Physics 1 2023. Thank you for spending your time watching this video, and I hope that you can support me by hitting the like button, or the subscribe button, I will keep continue making the video. Thank you so much, and I hope to see you again.